Hello friends, welcome to this third part of the application on the direct displacement based design of dual system. I wish you all happy Diwali. So in this third part we shall be seeing how this is applied for the calculation of the equivalent single degree of freedom system properties. I had discussed earlier there are a series of tables you have to prepare to get the different items related to the final computation. So the tables that I just mentioned are these: the table for the inflection height computation, table for equivalent single degree of freedom system computation, table for frame ductility computation, table for phase shear distribution. These tables are not very tough things. This can be done easily with the Excel sheet. These are actually pre-processing for the design. And finally, design has to be carried out through some established software. Out of this table, we have already covered the table for the inflection height, the first table. Today, we shall take up the case of the second table, table for the computation of the equivalent single degree of freedom system properties. The actual system is multiple degree of freedom system, and this can be converted to an equivalent single degree of freedom system. We have discussed this in earlier videos. And these properties are to be utilized gradually to get the other properties related to the design. We again take up the numerical example we started earlier, just I am showing it here. This is a 10-story building to be designed for 2.5% drift. Other required parameters are given here, and the relevant properties are also shown in terms of the symbolic representation: LB, HB, length of beam, depth of beam, then LW is the length of wall, which is 5 meters. So this you might be remembering from the previous video number PPT 14. In the video number PPT 14, earlier video, we had also taken up a table for the computation of the inflection height of the wall. So there we got the relevant properties which are important. I am encircling here. The overturning moment at the base for the frame, 23.74 kilonewton meter. Overturning moment or wall moment at the base of the wall is 11.491 kilonewton meter. And inflection height, which is important for today's tabulation, is 21.6 meter. So let us go to the today's table for the equivalent single degree of freedom system properties, converting the multiple degree of freedom system to equivalent single degree of freedom system, so that final all other steps will be taken up with this equivalent single degree of freedom system. So there are 8 columns in this table for mass, for height, for floor number also, then the yield displacement of the wall. We want to get the displacement profile of the system that could be obtained in the previous case of RC frame buildings by utilizing the shape profile which are available in the literature. In the case of wall, it is not shape profile that way, it is the yield displacement profile of the wall which are also available in the literature. Then next column is the product of mass and the delta I, Mi delta I, then Mi delta I square, and finally Mi delta Hi. So these parameters, if we calculate and take the summation of appropriate column, then finally we can find the properties of the equivalent single degree of freedom system. So the displacement profile delta I we just talked is given by this formula. Delta I, the displacement at ith floor level, equal to delta Iy, the wall yield displacement at that level, into this parameter theta d minus phi yw, h inflection divided by 2 multiplied by hi. Theta d is your design displacement in fractional value. Phi yw is the yield curvature of the wall. So for that appropriate expressions are available. Hinf is the inflection height of the wall that we have calculated in the previous video PPT 14, and Hi is the height of that floor from the base of the building. So how to get this yield displacement of the wall is given by two formulae. One formula when Hi is greater than or equal to H inflection, that is those stories which are lying above the inflection height of the wall. So this expression is available. And another expression when the height of the floor is less than the inflection height, the second formula. So you have to keep an eye on the level you are in and apply the appropriate formula out of these two. Yield displacement of the wall phi yw is given by simple formula 2 epsilon y by Lw. Epsilon y is the yield strain of the steel, so it is equal to Fy by Es. In this case it is 500 divided by 10 to the power 5 in Newton per millimeter square unit. So finally you get the phi yw curvature, yield curvature of the wall is 0.001 per meter. So this yield curvature or any yield value, yield rotation, etc. indicate the end of the elastic zone. So here the inelasticity sets in, and that's why it is the yield point. So this is your yield curvature. Yes, now we take up the tabulation for the computation of the equivalent single degree of freedom system. So this is the tabulation which has 8 columns we have just discussed. The different parameters are shown in the first row that we want to compute. The masses MI, this we have discussed in the video number PPT 14, so therefore I have just copied it. The height of the different floors also I copied from the previous video, so we are not showing the calculation here. I have divided this height series of the floors in two colors. So we know that our inflection height is 21.6 as I have shown in the previous slide. So a range where the height is more than 21.6 and a range where the height of the floors are less than 21.6 meter. So this coloration I have done for the sake of understanding and easy computation. Let us now find out the yield displacement of the wall, which is given by this expression. So this green zone is given by this green formula when height of the story is more than height of inflection. After this yield curvature, we need to put inflection height square. So star inflection height is 21 this, and this is also a invariant. So put a dollar sign. Now I am doing the bar here at the top. I don't know whether it will be nicely visible. And square of this, so put square. Then divide by 6. And this much for the formula. So it is 0.3002. So you can drag it over the other rows and you get the results for other rows. It is not all right. Why? Can you tell me? Because when it is below the is coming to negative value, which is not possible, because below the inflection height for this range you have to use different formula, which I have not done. So let me delete these lines. Yes, now let us take the case when the height of the floor is lower than the height of inflection of the wall. So this formula is applicable. Let us apply this formula. Equal to phi yw we'll put a parenthesis so that there is no confusion regarding division by 2 multiplied by hi square. So this square divided by 2 minus phi yw again we put a parenthesis to avoid confusion in the division, star height cube. So this column is D column and this row is 9, so D9 cube divided by 6 multiplied by inflection height. Yes, so we drag this formula downward, and these are the values of delta I, Y, yield displacement of the ball. Now we have to get delta I from this formula. Delta I equal to theta D minus phi by W inflection height by 2 multiplied by HI. Theta D is 2.5% or 0.025 in fraction. So let us apply this formula in column 5, equal to this one plus theta D is this, and you have to put a dollar sign here, minus phi by W into inflection height. Divided by 2. Whole thing multiplied by height. Some problem in the formula. What is the problem? Delta IY theta D minus phi by W. Inflection height is missing here. So this one, inflection height. This should be all right. Yes, so we can drag this formula, and these are the displacement profile for the different floors. Now multiplication etc. is very easy. Equal to mass into delta I and then again multiply by delta I get mi delta I square. So this is equal to this column multiplied by delta I. You need not take so many decimals. Yes, then mi delta I into hi. So equal to mi delta I is here, multiplied by hi is in this column. Then take the formula. Okay, now you require the sum of these last three columns. So equal to this sum. I can copy this formula over the other columns for getting the results. Yes, so these are the summation of mi delta I square, mi delta hi. So this I want to find this calculation of delta D. This formula is available, mi delta I square divided by summation mi delta I. So the delta D equal to this divided by this summation. Yes. Then ME is given through this formula, mi delta I by delta D, summation mi delta I. So equal to summation mi delta I divided by delta D that we have just calculated. The delta D is 0.541. So we put equal to summation mi delta I, this divided by delta D, which is 0.541. HE is given by mi delta HI divided by summation mi delta I, so equal to this one divided by this 24.69. So this is the way it goes. You check the formula again whether taken appropriately, and you can recalculate all these values to check the accuracy. In my personal calculation, I got the value of delta D etc. like this, 0.532, and ME I got 73302, and HE I got 24.324. So they are slightly differing from the values we have calculated. Maybe some mistake somewhere, possibly in the taking the heights in the formula. So these are the actual values of the results. A little change is found here, so some mistake. You can check it again yourself and recalculate and try to get this result finally. Thank you very much for coming up to here with me. The total computation is not big, but we have done it bit by bit, so it has taken a little time. The other two tables perhaps we can take in one day, in one video, and then the preliminary calculations will be over, and then we can go for the rest of the design part. So please subscribe the channel, like and share the videos, and put your queries and comments in the comment box. Thank you.